So, we will begin. Okay. As of now, we should be familiar with how to create our own Smith chart. There should be no issues with that. With the program that we have made, you should be able to create an impedance Smith chart and an admittance Smith chart. Okay. Once again, the plane in which we are seeing the Smith chart is a constant gamma plane. All right. The x-axis is the real part of gamma, which is the reflection coefficient. Y-axis is the imaginary part of gamma. Okay. And on the right hand side, gamma is going to be equal to +1. All right. If you see the coordinate axis, gamma is going to be equal to +1, corresponding to the entire voltage being reflected back, okay, from the load side. And the left hand side is gamma equal to -1. From the analytical case, we already know that this corresponds to a short circuit condition. So, what we had done was we had taken different values of R and X, okay, for the load resistance or the load impedance, and by fixing X to be constant, we varied R, and by fixing R to be constant, we varied X. Okay. When we fixed R to be equal to 0 and we varied X going from fully capacitive to fully inductive, we ended up getting this circle. Okay. Okay. R equal to 0 corresponds to the outermost circle of the Smith chart. Okay. Along this circle, you are just varying the imaginary part of the impedance. Okay. And then as you started changing R to say 0.5, 1, etc. So, R equal to 1 corresponds to the circle that passes through the middle of the Smith chart. The middle of the Smith chart is a specific point that is very interesting because the reflection coefficient is equal to 0. Okay. So, in most of the problems involving impedance matching, the goal is to navigate the Smith chart and arrive at the center of the Smith chart. Okay. So, this particular curve is R equal to 1 and the X changes from some minus 500 to plus 500 in our code, and we ended up getting this circle. So, these circles which are going from the outer side to the right hand side and reducing in radius are known as constant resistance circle. In each of these circles, the value of R is fixed and X is being varied. Okay. So, these are known as constant resistance circles. So, given an arbitrary load impedance of the form say 1 minus J2, suppose this is your ZL normalized, okay, with respect to your, then the procedure for finding this particular load on the Smith chart is to take the real part, find the circle which corresponds to R equal to 1. In this case, R equal to 1 is the circle that passes through the center of the Smith chart, the yellow curve here, all right, and then go for the constant reactance circle with X equal to -2. Okay. So, X equal to -2 is this circle, right. So, X equal to -2 will be somewhere here, right. So, this will be your intersection between the 2 points and you mark that as ZL. Okay. Once you have marked that point, the distance between the center of the Smith chart and the point that you have marked corresponding to ZL will give you the value of the reflection coefficient. Because you are in the complex gamma plane, the real part of it and the imaginary part of it can be measured separately, or you could also measure the magnitude of the reflection coefficient and you could take the angle from the horizontal axis and say that that will be the magnitude argument form of your reflection coefficient. Okay. Now, impedance Smith chart should be abundantly clear on how to navigate. Okay. The admittance Smith chart, what we had seen was by taking the reflection coefficient in terms of load admittance, okay, and writing a formula for the reflection coefficient. We generated these circles. The outermost circle corresponds to G equal to 0 or the conductance equal to 0, all right, and the imaginary part, which is the susceptance, is varied from negative to positive, and you end up getting a circle of constant conductance. Okay. Similarly, as you keep on increasing the value of G from 0 to 0.5 to 1, 1.5 all the way up to infinity, the radius of the circle shrinks to 0, okay, and the circle center itself moves to the leftmost position. So, you will end up getting a short circuit. This means that G is equal to infinity, okay, on the left hand side. Conductivity is equal to infinity means that you have short circuited your circuit, all right. You could also take the imaginary part of the admittance, which is going to be a susceptance, and keep your G constant and draw different reactance constant and different values of G, you will end up with the curves that are flaring out. So, these are circles of constant susceptance. Okay. So, given a load admittance, it will have a real part and an imaginary part. First you will find out the circle corresponding to the real part, then you will find the circle corresponding to the imaginary part, find the intersection of the two, that will give you your load admittance on the Smith chart. Okay. Now, one of the things that people do here is they flip this admittance Smith chart in both x and y axis, so that the circles exactly coincide with the impedance Smith chart and they maintain the same orientation. The only thing that they do is if they are dealing with admittances, they will switch the open circuit short circuit condition to the left and right side, and they have to keep care. Inductance will not be on the top, capacitance will not be in the bottom. So, they will invert the x and they will invert the y axis. But nowadays it is not necessary to do that. I prefer to keep the short circuit open circuit conditions in place, alright, because this is an imaginary gamma plane and it is tough to keep track of which axis you are looking at, alright. Just to be consistent, we do that. And today's class is more specifically on how to navigate the Smith chart, alright, and the application that we are going to look at is given a load, how we are going to match that load using different techniques and arrive at the center of the Smith chart. This is the objective. Okay. So, for doing this I am going to begin by using a tool. The name of the tool is going to be SimSmith. Okay. It is an open source free software that can be downloaded for multiple operating systems. It provides you detailed information on manipulating RF circuits with transmission lines, loads, and looking at the Smith chart interpretation. Okay. So, I am going to use this tool to demonstrate a few things, okay, so that it becomes clearer. Okay. So, I will start with SimSmith and I will go for the simplest circuit that we can have. The left hand side here corresponds to a source. Okay. Now, the source is a generator usually, alright, and it generates some power, alright. So, it does have a characteristic intrinsic impedance, okay. It does not come without any impedance, it does have an intrinsic impedance. Okay. Let us also remember that conventional transmission line cables also come in predefined characteristic impedances. It could be either 50 ohms or 75 ohms. Okay. So, your generators are made in such a way that the termination is 50 ohms. Okay. Now, when somebody says that this generator is going to generate say 1 watt of power, the meaning is at this end, if you matched the impedance of 50 ohms, you are going to be getting 1 watt of power dissipated on the load. That is the meaning. The rated power of a generator means that after your internal impedance, if you connect something on the outer part of this circuit, and if this impedance is matched to this impedance, then you will be getting 1 watt of power. Okay. So, what I am going to do is I am going to set the parameters of the generator, I am going to tune the parameters of the load to make this point clear first. Okay. So, here we are not putting any transmission line, we are starting with really basics. Okay. So, I am having a 10 megahertz alternating source on the left side. It has an intrinsic impedance of 50 ohms, purely resistive. Okay, and I have connected a load and I am going to make it 50 ohms. Okay. Once I make it 50 ohms, the meaning is this is a 1 watt generator, it will provide me 1 watt at the load. Okay. So, W1 means that I am going to be having 1 watt at the load because the impedance is matched. Okay. That is the meaning. But one could go ahead and still analyze it in more detail like we do in circuits, say that there are still 2 resistances, alright. Maybe the generator is generating more power and half the power is being dissipated on the load and all that. But we have to be clear that we are not going to be creating generators with 0 ohms internal impedance. It is going to be standard, it is going to be some internal impedance and most likely it is 50 ohms. Okay. So, when we talk about the power on the load and impedance matching condition, we are talking about how much of power will be dissipated here, and if this load is matched to this, we are going to be getting the rated power of the generator. Okay. Now, if you can always tweak this, you can say that I will connect 500 ohms, alright. You will immediately notice that the power that is coming to the load is 0.331, which is less than 1 watt. Okay. And you will have a standing wave in your circuit. right, which can be calculated by ZL minus Z0 by ZL plus Z0. Okay. Correspondingly, you will be having also a reflection coefficient. Okay. Now, if you have mismatched loads, you will not be drawing the rated power from the generator on the load. Okay. So, since this is a problem relating to signals, all right, power is very critical, signal power is very critical, you cannot afford to lose signal power. Okay. An example can be on the left hand side there is an antenna, on the right hand side you have a speaker or something that is processing this signal. You do not want to lose signal power anywhere else, that is the whole objective. So, whatever is the rated power, we would like to get it on the load, that is the objective of impedance matching. Okay. Now, we can start with a simple case and we can deliberately start with we will start with identical case, matched impedance. Okay. On the right hand side we have a Smith chart, okay, similar to what we have generated, constant resistance, constant conductance circles, right, and then you have constant reactance and constant susceptance circles, all of them are present in this Smith chart, and in the center we are having a green and a blue dot. Okay. The green part corresponds to the generating portion after the internal impedance, that is you are looking in from this portion to the right side, okay, and the blue part corresponds to the load impedance. Okay. Since the load impedance is 50 ohms, it is normalized with respect to the 50 ohms intrinsic of the generator, okay, and the result load impedance is equal to 1. Okay. Now, you have to look for the intersection of resistance equal to 1, which is the circle passing through the center, reactance equal to 0. That means you will mark the load resistance at the center. That is what has happened over here. Okay. Now, we can make this slightly different, say 25 ohms at the load. Now, we notice that the representation of the load impedance has moved to the left hand side of this Smith chart. In this Smith chart, the normalizing resistance Z0 that we are using is 50 ohms, okay, which is the intrinsic impedance of the generator itself. Okay. So, with respect to this, the load resistance is half, which means that you have navigated to the left of the Smith chart. Okay. So, your load impedance representation is over here, okay, and one can also look at the standing wave ratio, it is 2. So, you can say that it is 25 minus 50 divided by 25 plus 50, okay, and you can find out that the standing wave ratio is going to be 2. Okay. Okay, so 25 minus 50 by 25 plus 50 will give you gamma. Okay, then you have to do 1 plus gamma by 1 minus gamma to get the standing wave ratio, and that is going to be equal to 2. So, I will just draw a standing wave, constant standing wave ratio circle. So, what has happened is in the Smith chart, if you draw a concentric circle with respect to the axis of gamma plane, right, you are going to be ending up with a circle that gives you constant voltage standing wave ratio. All along these points, the magnitude of gamma is identical. So, 1 plus mod gamma divided by 1 minus mod gamma is identical throughout the circle. So, if your load impedance is moving around this circle, your circuit will experience the same standing wave ratio. Okay. Now, once I have this, the question that can be asked is, how do I make the impedance as seen from the input side? Generating side is over here, all right, looking into this direction should be 50 ohms, so that I do not get 0.889 watts as put over here, but I get the entire 1 watt. This is the objective of impedance matching, all right. Now, the horizontal axis of the Smith chart over here also corresponds to reactance equal to 0. Okay, it is a constant circle with infinite radius and reactance is equal to 0. Okay. If the reactance is equal to 0, navigating along this circle, all right, navigating along the x direction, if I keep changing the resistance, I will go along that particular path. So, I can say that a solution to match the impedance can be simply to add a series resistor in between like this and make the value of that resistor to be 25 ohms, so that a combination of 25 and 25 will add up together to produce 50 ohms. And when looked from the generating side, it looks like it is 50 ohms. So, it is impedance matched, all right, and you will immediately notice that the point in the Smith chart has moved to the center. Okay. So, the blue part is the load, okay, normalized with the 50 ohms, which is where it was originally before we added another resistance. The resistance is the green part, this graph is very interactive. It shows that because you added a green color part, it moved from the load to this point as seen by the generator. Generator is pink color corresponding to the pink color in the circuit. So, from the generator side, it sees that the circuit is fully impedance matched, okay, and it has no reflection coming to the generating side at all. So, the standing wave ratio it sees is 1, reflection coefficient is 0. We have an impedance matched circuit clearly. Unfortunately, while doing this impedance matching using a resistor, we moved along the constant reactance circle, we changed the resistor, and we know that resistors will dissipate electrical power into heat power, right. So, which means that incoming power over here was 1 watt as seen here, half the power has been dissipated here, only the remaining half is available for your load, okay. So, now the question becomes, have you impedance matched and have you attained the objective? If the objective is to not have any standing waves or not have any reflection coefficient, you have done the job, alright. However, by doing this, we have actually worsened the amount of power that is available on the load, okay. If I made this 0, which would be short circuit, okay, I actually had 0.889 watts being dissipated on the load, and by going to impedance matched condition, I actually reduce the power that is dissipated on the load to 0.5. So, the objective of impedance matching has to become very clear. It is not only to minimize the standing wave ratio or the reflection coefficient, it is to make sure that the rated power, the maximum power that is possible is actually dissipated on the load, right. In this case, half the power is dissipated on the load, right. So, what we are seeing is if we add a resistor in series, it is going to draw some power, and under the impedance matched condition, it is going to dissipate some amount of power, okay. Now, this particular example assumed that your load resistance is less than the intrinsic impedance of the resistor. So, you could add a series resistor, right. So, let us go ahead, remove this part again. We will make our load resistor higher, okay. So, we will make it double. Previously, we had half, now we will make it double, okay. Load resistance is double, okay. So, the load resistance normalized with respect to the intrinsic impedance of the generator 50 is 2, okay. So, you have to look for the circle where R is equal to 2, R equal to 0 is the outside circle, R equal to 1 is the circle that passes through the center of the Smith chart, R equal to 2 is the next circle that is following it. Reactance is equal to 0, that means the horizontal axis is the intersection. So, this is your representation of load impedance on the Smith chart, okay. It is present over here. Now, I cannot add a series resistance to match the impedance, because a series impedance will only move this to the right hand side more and more, okay. So, I need to add a resistance, but maybe I have to add it in shunt, okay. I have to add it in shunt, okay. If I added it in shunt, alright, and if I kept on increasing this value, if the resistance in the shunt path approaches infinity, that particular arm will become an open circuit, okay. So, entire current will flow only through the load, and you will not be moving the resistance seen by the generator part. So, you need to know you need to adjust the values, okay, and as you start reducing the amount of shunt, okay, it will go all the way to the left hand side of your Smith chart, okay. If the conductive path here is having negligible resistance, almost no current will flow through the load, okay. That means that you would have short circuited, and the representation that is seen by the generating side here is a parallel combination of a short circuit and a load, which is short circuit. So, the reflection coefficient goes to -1, okay. So, in order to match it, I need to find the correct value of resistance to put. So, I keep increasing the value of resistance till I reach the center of the Smith chart, okay. Okay, somewhere about that. If you see, the reflection coefficient is 4.37 milli, standing wave ratio is 1.009, and the power once again is 0.50 watts, okay. So, if I zoom in and if I make it even more correct, so this is 100.8. So, I can make it 100 ohms, because 100 ohms and 100 ohms in parallel will become 50 ohms, 1/2, okay. So, I will make that. Okay. So, now what happens is the circuit is impedance matched, standing wave ratio is only 1, reflection coefficient is 0, but I still have only 0.5 watts at the load. Okay. So, once again, by adding a resistor, you moved in the line of constant reactance. In this case, the reactance is 0, so you moved, but adding a resistor comes with a penalty in terms of the power that you can get at the load end. Okay. So, now the question can be, can we take a purely resistive load and make it appear at the center of the Smith chart as seen by the generator, but have all the power dissipated at the load? Okay. So, this means that we cannot use resistors, then we are left with two other options. Okay. We can either do, so I will go back to 25 ohms. Okay. We can do two things. We can add, say, inductors and capacitors and try to understand the meaning of the two. Okay. So, the first thing I will do is try to add a series capacitance. Okay. So, this is the load representation on the Smith chart. Once you add the capacitance moves the load as seen by the generator in the negative direction, because it is minus jXc, right. So, it is going to move it to the negative direction and your reflection coefficient is going to change. So, this is the impedance as seen by the generator. This is going to be your load impedance actually before adding the capacitor. So, the green part is the capacitor, it moves it along this side and the generator sees this part. Okay. Now, I understand that if I keep on changing the value of the capacitance, alright, I am increasing the value of capacitance to be very, very large. If the capacitance becomes very large over here, right, you are approaching the reactance part to be approaching to infinity, right. No, capacitance is very large, then you are making it actually a short circuit, alright. So, that means you will see the effect of only the load, and so the point converges to the original load impedance. So, again we can make a change to decrease the capacitance. Okay. It traverses along the point of constant resistance. Okay. 25 ohms corresponds to R equal to 2, alright, and you are changing the capacitance, it sweeps the same place in this, same circle and reaches all the way to the right hand side point. Okay. So, adding a series capacitance, you can do some level of thing, you can go in the half plane below and you can go along a constant resistance path. Okay. Another thing that one can do is they can add a capacitance in parallel instead of series, right. Once you add in parallel, you will be able to go along constant conductance path. Okay. So, if you keep going this way, the negative half, you will reach the other side. So, with the capacitor, you will be able to go either this way or you will be able to go this way, depending on whether you connect it in series or in shunt. Okay. Now, in order to reach the point in the middle, one of the most important things is we have to come from the load, we have to say come down. If you are going to add a parallel or a series capacitor, you will be coming down on the negative half plane and you will have to intersect one of the circles which goes through the middle of the Smith chart. The goal is always to come to the middle of the Smith chart, and there are two circles which are intersecting corresponding to R equal to 0 or G equal to 0. Both of them pass through the center of the Smith chart. On top of that, X also is equal to 0, the horizontal axis. Okay. So, you have to arrive here. So, you have to reach one of these 2 points and arrive at X equal to 0. This is going to be the objective. So, we can also see what the inductor does. A series inductor will move the point to the top half plane. As you keep increasing the inductance value, it will go towards the right hand side, alright, as seen by the generator. And if you make this a parallel inductor, right, okay, you can go to the left hand side. Okay. So, these are the combinations possible, and one can go ahead and try to do the impedance matching without using a resistor. Okay, and we can see the consequence. Now, what we will do is we are having a parallel inductor already moving in this direction, alright, and we can always connect a series capacitance. Okay. We could do that. So, the green part here is the capacitance connected to the load, side, okay, and this pink part is corresponding to the inductance that you have connected over here. And if you are able to adjust the two parameters, you will be able to arrive at the center. Okay. So, what we can do is we can start manipulating things, all right. So, I can start increasing the inductance. To reach the horizontal axis. Then I can go to the capacitance part and manipulate the capacitance, right, to see how I can traverse. Okay, there we go. It's approximately, can zoom in and do a fine tuning. So, one of the things we notice here is the load was present here, which is the blue. Okay. To the load you have connected a series capacitor which pushes it to the negative half, okay, and it comes and it actually intersects G equal to 1 circle first. Okay. You are hitting the G equal to 1 circle. Once you have done that, you are adding an inductor to go above, and then you are hitting this center of the Smith chart where the reflection coefficient is equal to 0, all right. And if you check the power that is available at the load, since L and C do not consume any power, you are having 1 watt, which is the rated power of the generator, appearing across the load. Okay. Now, this is not the only way. You could also do this in multiple ways. For example, you could always have, so let us say, could have a capacitor and an inductor like this, all right. So, previously we had a capacitor connected to the load in parallel, you could always replace that with a series inductor, all right. So, the first point where you will travel, before you are traveling downwards hitting the G equal to 1 curve, but since you have connected an inductor, you will be traveling upwards, and the goal can be to meet this circle once again and then traverse down to the center. Okay. So, we can adjust the value of the inductor . Okay. So, incidentally with some minor adjustments to the capacitor, I will be able to get a standing wave ratio of about 1, all right, and the power that is available on the load is about 1. Okay. I can do it very precisely, but I am not able to do it with the mouse over here. Okay. So, this is operating at 10 megahertz. One can always go ahead and calculate the value of the reactance for these frequencies, and then they can see what is the value of the inductive and the capacitive reactance and how they cancel out each other. Okay. This is the most elementary way of doing some impedance matching. Okay. Now, we notice that the resistance will move you along the path of circle of constant reactance if your load is purely resistive, all right. Then adding any series or shunt resistance will move only in the horizontal axis of your Smith chart. If your load is complex and if it is somewhere else, and if you add resistance, it will go in the along the circle of constant reactance. Okay. So, but adding a resistor is actually going to come with some penalty, because you are going to lose some power, but adding an L and C will not give you that penalty, and it will allow you to dissipate all the power at the load. This is the most elementary way of doing impedance matching in a circuit. Again, now we have to understand what will happen with the transmission line, okay, and then I will introduce a transmission line between the source and the load, all right, and there are some parameters for the transmission line that I am going to change. First of all, I am going to make this a lossless transmission line, okay, and I am going to keep the transmission line characteristic impedance to be matched to the generator. Okay. Most of the times the generators have some ratings, they are operating at some frequency and they are supposed to have some termination. Here we are assuming a 50 ohm intrinsic impedance for the generator. Transmission lines widely available for 50 ohms or 75 ohms. In this case, we are choosing a 50 ohm transmission line cable. It is a 50 ohms standard cable. The load is what we are trying to match. Okay. The load can be something else. Okay. So, here there are a few things that we are noticing. Okay. It says that 0.667 velocity factor. Velocity factor means that the speed at which the waves are going to be traveling in this transmission line with respect to the speed of light in vacuum. So, assuming that the speed of light in vacuum is 3 times 10 to the power 8 meters per second, okay, 0.6667 means that the velocity will be 2 times 10 to the power 8 meters per second. So, in this transmission line 1 by square root LC will correspond to 2 times 10 to the power 8 meter per second, okay, which is almost practical. I mean, that's how that's the velocity of a signal in a transmission line. Now, one of the things that we noticed is the load is present here connected to a transmission line. The transmission line moves the impedance point from the axis over here to 90 degrees above like this. The angle of phase that the transmission line is providing is only 45 degrees. Okay. So, the transmission line is providing only 45 degrees phase, but it is moving the impedance seen, all right, by, I mean, the angle of your reflection coefficient is going by 90 degrees, all right. It is simply because we know the formula for the reflection coefficient. It has gamma at load e to the j 2 beta L. Okay. So, beta L, if it changes by 45 degrees, the angle of the reflection coefficient will change twice of that. So, for that reason, all right, there can be some confusion when you are reading the Smith chart. If you traverse around the Smith chart, okay, all right. So, if I go for 90 degrees to be the phase provided by the transmission line, I will reach the diametrically opposite point in reflection coefficient, 180 degrees change. Okay. So, the entire Smith chart can be traversed with 180 degree phase shift of your transmission line. It will form an entire full circle. Okay. So, this is one thing that we have to register in the mind. The second thing is, now we have gone over the transmission line, all right, and we have provided a 180 degree phase shift to the signal, but you have reached the same point on the Smith chart. Okay. 180 degrees corresponds to lambda divided by 2, okay, which means that in a transmission line, as the length changes, the impedance will repeat itself after every 180 degrees or lambda divided by 2, okay, which is consistent with what we had seen before. Okay. So, we had short circuit and open circuit terminations for the transmission line, and we saw that at every lambda over 2 there will be a zero crossing in your impedance in the length of the transmission line. So, every lambda over 2 the transmission line parameters will again start to match in a lossless case. Okay. So, the actual length of the transmission line really does not matter, only the electrical length matters. Electrical length is beta L, beta is your phase constant multiplied by L. So, it has to sweep at 2 pi. Okay. So, a transmission line does something very different from L and C individually, right. It has a tendency to move around the circle of constant VSWR. Previously, you were either moving in a constant circle of resistance, conductance, reactance or susceptance. A transmission line will move along the circle of constant VSWR. This means that whatever be the length of the transmission line that you are going to be choosing, okay, the VSWR seen in the transmission line is going to be the same, okay, but the impedance that is seen could be different, the length depending on the length of the transmission line. So, if you have a length that is like this, your generator will be seeing impedance at this point, all right, instead of your load impedance is here, but the generator sees a diametrically opposite impedance connected to it, right. So, you know, one of the things that we see is for a purely resistive load, okay, in order to reach the intersection with the same line again, all right. So, here it is purely resistive load, x is equal to 0, and if I use a transmission line just with 90 degree phase shift, okay, 90 degree phase shift, I reach the horizontal axis again, all right. Now, I would like to bring this load as seen by the generator to the center of the Smith chart. I cannot adjust the length anymore, I will have to adjust some other parameter, okay. The some other parameter can be the characteristic impedance of the transmission line itself. So, I can start say increasing and seeing what happens. So, it goes further away. So, that is not the correct direction, and I can start decreasing the characteristic impedance, and I will notice that it stays on the line, I mean it stays on the horizontal line, but it keeps going towards the center of the Smith chart. now I have matched. Okay. So, I am noticing that the power available to the load is once again 1 watt, okay, and I am providing a 90 degrees phase shift. So, this is a lambda over 4 length transmission line cable, it is a quarter wavelength cable, and if its characteristic impedance is 35.3, okay, I am getting an impedance match as seen by the generator. Okay. We can make a quick calculation for this. We can take the impedance which we are using for normalizing, or the intrinsic impedance of the generator, which is 50 ohms, okay, and we can take the load that we are trying to match, which is 25 ohms, okay, and take a square root of this. Wow, okay, that is 35.3553, okay, 35.3553. So, I am close, 35.33, okay. So, it seems that there is a relationship between the characteristic impedance of the cable that you have to use and the product of the characteristic or the intrinsic impedance of the generator and the load. So, the relationship that seems to be seems to be followed, okay, is Z matching for the transmission line seems to be equal to Z generator multiplied with ZL. Okay. This is what seems to be happening, okay, and this can be easily proven. You can take your equation for Z in that we had written before, all right. So, we had written the equation for Z in, okay. So, you have Z naught times ZL plus Z naught tan H gamma L divided by Z naught plus ZL tan H gamma L. This is for a lossy transmission line circuit. For a lossless transmission circuit, you will remove the hyperbolic part, all right, and instead of gamma you will simply write this as beta L, okay. Now, beta L in this case corresponds to the electrical length that you are using. Beta is going to be 2 pi divided by lambda. So, I will make some simple substitutions. So, this is Z naught multiplied by ZL plus Z naught tan 2 pi divided by lambda is the phase constant times L. L is here lambda over 4, okay, divided by Z naught plus ZL tan 2 pi by lambda by 4. Was it? Oh, J tan beta, sorry. Okay. Technically, it does not matter whether you have J or not, because the tan pi by 2 it becomes, so sin pi by 2 divided by cos pi by 2. So, that is anyway, but so here you will be having 2 pi divided by lambda times lambda divided by 4. So, that becomes tan pi by 2, okay. Tan pi by 2 is infinity, all right. So, this is not going to be easy to do it in this way. That means that we have to normalize with respect to this term. So, we can divide the numerator and the denominator with some tan pi by 2 and we can see what happens, all right. So, Z naught will just become, here this term will become 0 plus J times Z naught divided by 0 plus J times ZL, okay. So, I can cross these two off, right. I have Z naught square divided by ZL is equal to the Z input, right, which implies that the Z naught is going to be equal to square root of ZL Z in. In our case, Z in is nothing but the impedance as seen by the generator, okay. So, it seems to be following the geometric mean, okay. So, which is what we have arrived at using a Smith chart, okay. So, the approach that we have taken is that of a quarter wavelength transformer. This is commonly known as quarter wavelength transformer. I will go back to this diagram. You will have a 90-degree phase producing transmission line of a characteristic impedance, which is the geometric mean of this input impedance here and your load impedance, and then that is going to produce impedance matching. Remember that we have taken lossless conditions. So, we are starting with the horizontal axis and ending at the horizontal axis also. Okay. So, this is a straightforward case, but what are the merits and demerits? Merit is okay, it provides me with all the power at the load. The demerit is it is not easy for you to go and buy a cable which has 35.33 ohms characteristic impedance. So, it is good to understand that it can be done, but a practical approach is just connecting L and C at your load and actually trying to match what is going to happen. Okay. Are there any other ways to do this? Yes, there are multiple ways of doing this, but before going there, let us also see some more details, okay, as to what the cases can be. Okay. So, first what I am going to do is, for now I have assumed the load to be real. Okay. I am just going to make this load to be having a real and an imaginary part, and then I am going to work backwards as to what all I can do. Okay. So, I am going to be taking a load which is say 35 minus J 47.5, and I am going to get rid of the transmission line first. I am going to start with the conventional approach and then the transmission line based approach. Okay. Now, the load impedance is not on the horizontal axis. Okay. It is not on the horizontal axis. That means that it is clear that you have to do some reactance manipulation also. Okay. You will need to add some passive components and you will have to add some reactive components. The resistor will get you along the circle, alright, but you will still need to get here. Going up the here needs some L and C. Okay. So, what we could do is we could start with say series capacitor, say we put some parallel inductor and see what happens, right. This is the load. Adding the inductor in parallel moved along the conductance circle upwards, and adding the capacitor in series made you go along the constant resistance circle downwards. Okay. This was not intentional, I just plugged in, it seemed to happen, but since it is happening I am going to manipulate it, alright. So, I am going to start with just playing with the inductance values. I already matched. Okay, is close. Standing wave ratio is 1.004, can assume it to be 1. Reflection coefficient is 2.24 milli, this is almost no reflection, and the power available at the load is 0.988, can take this to be 1 watt. I have matched a load which is not resistive using only L and C. Okay. This is one way of doing it, alright. You could also think of doing this in other ways, alright. The other ways, one of them will involve say simple transmission line approach. Okay. So, I am going to remove these two components. Okay. Now, I know that I can impedance match with L and C, there is no issue. Now, I want to understand what a transmission line will do over here, alright. Remember that just like your generator, the transmission line has a characteristic impedance of 50 ohms, okay, which is practically procurable, right. But let us say that since we have done quarter wavelength matching before for a purely resistive load, what happens when the load is complex? Is it possible to still match with the transmission line? This is the question. Okay. Let us have a look at it first and then see whether it is possible to match or not. All I am going to do is I am going to change the length and I am going to change the value of Z to see whether I am able to arrive at the center of this Smith chart. Okay. So, I am going to do this. Okay, I am getting away from the center. So, I am going to go the other way and see how close to the center I can get with this. Okay, I am able to get towards the center, but I am not able to go down, alright. To go down, I know that I will see what happens. Okay, getting there, right. Okay, some manipulation. Clearly looks like it is not going to be easy to do this. Okay, it is not going to be easy to do this, that is what I am saying, alright. In some loads it may be possible to do it, but it is not going to be easy to do this, right, because there are two parameters. First you have to figure out the length, and then you have to figure out the characteristic impedance, and you are having a real characteristic impedance that is transformed to some part, and then it has to be matched to the load and then create a impedance of 50 ohms. So this quarter wavelength matching is good for resistive loads. It is not very good for complex loads. Then what could be the approach? I mean, I want to be able to match a complex load, but I want to use only transmission lines. That is all I have to match. The approach is, we can think about it in this way. Suppose I go back and I make the characteristic impedance to be 50 ohms. I try to understand first what the transmission line can do for me. Okay. So I keep increasing the length of the transmission line. So I'll just, okay, yes, it goes to the horizontal axis, which means that if I use a small portion of transmission line, I can make the complex load look like a resistive load at the generator, because it cuts the axis over here. I will use a small section of the transmission line of 50 ohms, which is matched over here, to make it look like it is actually resistive with respect to the generator. Then I will add another transmission line section. Okay. I will add another transmission line section, all right, and I will make that 90 degrees. And then I will manipulate the characteristic impedance. Oops, I am in the wrong path. No, this has to be in this way. Okay. I will make it 90 degrees and then I will keep adjusting this. It is possible to match. Okay. Suppose you want to use a quarter wavelength transformer like this, you will have to bring the complex impedance, load impedance, to the real axis first. You can use a transmission line to do that. Okay. A transmission line will take you around in circles of constant VSWR, and the constant VSWR circle cuts the x axis two places, all right. So you can use either of them, and then you can use a quarter wavelength transformer after that to match. Okay. So a complex load can also be matched with the quarter wavelength transformer, provided you figured out that the complex load can be made to look resistive first with respect to the generator, then you use a quarter wavelength transformer to match. Okay. It is a slightly tedious process, but again the absurdity of doing this is, granted that you will first bring the load to the x axis. That is done using a standard cable, say 50 ohms cable. Only the length has to be adjusted, which we are okay, can be done. But then finally to do the matching, you still need something with a Z0, which is 28.93 in this case. So you will have to manufacture a specific kind of a cable to do this again, right. So the quarter wavelength transformer, though, can be used for bringing complex loads to the matching condition, you will still need to make custom cables, and in many cases this is not going to be possible. So the better approach is keep everything standard, only the load is going to be changing. How are we to match the load? There are two techniques, or there are multiple techniques actually to do it, all right. With the transmission lines itself, people use what is known as a single stub technique and a double stub technique. Even within single stub they have open stub or shorted stub, all right. Some people call it series stub or shunt stub. Okay. So you have then the double stub technique. Okay. Now what I will do is, I will not go over the technique in great detail, but I am going to show you how it works, all right, and probably you can also start approaching impedance matching problems in this manner if you are going to make some hands-on experiments. This is what a person would actually do, right. So I am going to first remove the abnormal portions of the I am going to remove both these transmission line sections. Okay. I am going to add a transmission line first. Okay. Now this transmission line connected to the generator, I want to make it look, it's like long, it is like a long transmission line. So source is present somewhere, the load is present somewhere else. It's quite a long transmission line. 45 degrees seems really small, so I want to be sure that it's a fair enough transmission line. So it's 2.4 meters. Let's say I want it 30 meters, which is realistic. Okay, so let's say that I want to make this 30 meters. Now, one of the things that I noticed when I did this by default is, instead of cutting the same circle again and again, it is spiraling inwards. In this case, the spiraling inwards is happening because of the loss in the transmission line. The transmission line is lossy, and if it is lossy, okay, in the Smith chart, with every 360 degrees you are going to keep spiraling inward, 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 etc. Alright, and finally you will reach the center. The amazing thing is, if I make this really long, say 300 meters long, actually I am getting closer to the impedance match condition. If I make it very long, say 3 kilometers or something, I may actually be very close to the center. The generator will not see any reflection, but the load also will not see any power. Okay, so one has to be very careful about using lossless transmission lines. Okay, otherwise many things can happen. The sender will believe that they are sending the signal, since they are not getting any reflection, it's going to the receiver, but the receiver will have the belief that there has been no signal sent, simply because your transmission line is eating all the power. Okay, so this is one way of impedance matching, which should be totally avoided, because you have matched the impedance in the worst possible manner. You have used more material to achieve the least amount of power delivered possible. Alright, so what we start with is a lossless transmission line. So I'll just make this 0. Now it looks like we can do something. Okay, so a lossless transmission line is going over the same circle multiple times. Okay, now a short, I could connect a stub or a portion of a cable, alright, in parallel to it. I am starting with shunt stub. Okay, I want to attach this shunt stub here. Okay, the manner in which it is connected looks like it is directly in connection with the load. There are two parameters that we will have to work out in this shunt stub. The first parameter is how far away should it be from the load, and the second is how long this cable which is shorted itself should be. These are the two parameters. Okay, so it is possible to match. I will show you in a minute how to match. Okay, but the two unknowns in this kind of single stub matching is the length of this stub itself and the distance from the load where this stub has to be inserted. But the good thing is we are using only standard components. So 50 ohms characteristic impedance for all the components. That is the advantage. So if I have to control the distance from this, what I will do is I will put another transmission line at the end like this to clearly signify that from the load there is a distance of an ordinary transmission line, and at that distance I have a shorted shunt stub. After that there is a very long cable. So towards the load end I am measuring from the load some distance, standard cable, and then I am having a parallel shunt stub. Okay, and then I am having a very long cable to the left side. This is the setup. Now we have to just manipulate two things. We know that only two things are present. One is the length at which you have to insert the stub, length of the stub itself. Alright, so you can start with this particular case. Alright, and then you can start playing with the length. You can increase or you can decrease. So I'll just see, you can do this. So what we are aiming for is red color corresponds to generator now. So suppose we have added more components, red color corresponds to generator. This red point has to come closer to the center of the Smith chart. Whatever allows you to do that, you can do it. So I am starting first with this part. Okay, I am going to be changing the length of it. Okay, I get closer to the center, I keep getting closer and closer and closer and closer, and then it starts going away. So I'll just get to the point where it was close to the G equal to 1 circle. I'll stop there. Then I will get to the short circuit stub and I can manipulate its length, that's all, right. So I'll just see whether I can increase, or so if I increase the length of this, it gets away, the red color point is getting away from the center. If I keep decreasing, almost there, okay. So, in this case the load was moved along a constant VSWR circle by a standard transmission line. A shorted parallel stub moved this to the center. Okay. This process is known as single stub matching. You can also print the Smith chart and do it in very tedious ways, but I prefer to keep it in this way. When we are talking about single stub matching, that is all. You just attach a section of the transmission line at the end, figure out how long it should be, and then figure out what is the length of the shorted stub that is supposed to be placed, and then manipulate till you are able to see the impedance go to the center. If you want to do it using a printed Smith chart, there are many tutorials available on the internet. You can go ahead, you can take a complex load. In this particular case, I have verified, I have taken the specific value from a problem in the book, okay, and I have seen that my solution is exactly matching. Okay. This is the simplest way and it will give you a feeling for what is happening. So, my suggestion is go back, install this program again, try to do all the gimmicks possible, vary everything till you understand what is going on. This particular tool provides you the ability to manipulate things and understand what is the effect of one thing on the Smith chart. This is single stub matching. Okay. So, I will stop here.